Let's look at section 12.3, logarithmic properties. The first property we'll look at today is called the product rule for logarithms. For any positive real number, b not equal to 1, and any positive real number x and y, log base b of x plus log base b of y is equal to log base b of x times y. What we are saying is, if we have the addition of two logs with the same base, we can multiply the arguments into one larger log. Let's look at example 1. It says combine the expression into a single logarithm, and we'll use the product rule. I can use the product rule for the first two terms. Log of 5 plus log of 7 is log of 5 times 7. And then we'll add log of x. 5 times 7 is equivalent to 35. And now we could add log of 35 plus log of x using the product rule, which means we could multiply the arguments together. So this is log 35x. I could also use parentheses around the 35x so that the reader knows the argument is 35x. Let's look at part B. We can do the same process since all of the bases are the same. And so I could write this as log base 3 of 8x by multiplying the first two arguments. And then I can add log base 3 of 8x plus log base 3 of y. This becomes log base 3 of 8xy. And that completes part B. In part A, we want to undo the product rule. I could write this as log base 2 of 5 plus log base 2 of b. We can't simplify log base 2 of 5, so we'll leave that alone. And we can't simplify log base 2 of b. And so that's it for part A. Looking at part B, I can use the product rule twice. I could write this as log base 3 of 27 plus log base 3 of x plus log base 3 of y. Now on the right side we have log base 3 of x plus log base 3 of y. That can't be simplified, but this part can. We know that 3 cubed is equal to 27. And recall, the answer to the logarithmic expression is the exponent. So this entire quantity, log base 3 of 27, is exactly 3. We have 3 plus log base 3 of x plus log base 3 of y. Now this is completely expanded. In the next property, this is known as the quotient rule. For any positive real number b not equal to 1, and any positive real number is x and y, we say log base b minus log base b of y is equal to log base b of x divided by y. This is the quotient rule. For addition, we are multiplying the arguments. For subtraction, we're dividing them. In part A, I can use this to divide 60 by 15. And this simplifies to log base 2. 60 divided by 15, that's 4. But we're not done yet. We can simplify log base 2 of 4. Recall 2 squared is equal to 4. So this log base 2 of 4 is equal to 2. That's the exponent that I need. In part B, we'll take the natural log and divide x by 8. And since I cannot simplify that any further, this completes part B. In example 4, we're doing the opposite. Let's expand the logarithm. In part A, we'll take log base b of x and minus log base b of b. This can now be simplified. The right side, the log base b of b, is asking b to what power gives us b. That means the right side is equal to negative 1. We know an exponent of 1 will give us b back, and so log base b of b is equal to 1. In part B, I'll use the quotient rule. We'll say log base 4 of x minus log base 4 of 64. The left side cannot be simplified, but the right side can. 4 to what power gives us 64? I know 4 cubed gives us 64, and that means log base 4 of 64 is 3. Another property is known as the power rule. For any positive real number b not equal to 1, and any positive real number x, and any real number r, we have log base b of x to the rth power is equal to r times log base b of x. What does this property say? Well, it says if you have an exponent inside the argument of the log, you can bring that to the front. That's what it's saying. Or if you have a number that's multiplied in front of your log, you can bring that to the exponent inside the log. That's a useful property because we can expand logarithms now. Let's expand this log. Log base 3 of 9 plus log base 3 of x squared plus log base 3 of y to the 4th. I use the product rule twice to expand the log, and now I can use the power rule. I could bring that 2 to the front. I could bring that 4 to the front. Log base 3 of 9. This is 2. 3 squared gives me 9, so this is 2. We'll bring that 2 to the front. That's 2 times log base 3 of x. Bring that 4 to the front. That's 4 times log base 3 of y. In part B, we'll start with the product rule. This is the natural log of a to the 8th plus the natural log of b to the 9th plus the natural log of c to the 20th. And I can use my power rule to bring that exponent to the front of our log. This gives us 8 natural log of a plus 9 times the natural log of b plus 20 times the natural log of c. And we can't simplify it further, so that's it for part B. In example 6, we want to rewrite using the power rule, so going backwards. I'll take that 8, bring that up into the exponent. This is equivalent to log base 8 of x raised to the 8th power. Same thing for part B, we'll use the power rule, bring that exponent to the top. This is log x to the 5th power. We have another property. It states for any positive real number b and any real number r, if we have log base b of b raised to the r, that's equal to r. Now, why is this property true? It's saying if we have a base b, what power do I need to raise it by to give me b to the r? Well, that missing exponent has to be r. That's what this property is saying. Essentially, the definition of what logs are. It's the exponent that you need to raise the base by to get the argument. In example 7, part A, we're looking for the natural log of e to the negative 4. Well, this means if I use the power rule, I could bring that negative 4 to the front. This is negative 4 times the natural log of e. And a nice thing about the natural log of e is the base is e. E to what power is equal to e? Well, that's 1. So the natural log of e is equivalent to 1. So this is just negative 4. So our property gives us negative 4 as an answer right away because the base is the same as the base of the argument. But we could also use the power rule to get the same answer. Using the previous formula, we can get the natural log of e to the 7th. Again, you could bring down that 7 to the front. 7 times the natural log of e. The natural log of e is just 1, so this does give you 7. Let's simplify the expression e raised to the natural log of 16. We can simplify this because there is a property of logs. We can say b raised to log base b of r. Well, that's equivalent to r. And so I can just write my answer out as the argument. We have e raised to the natural log of 16 is 16. In part B, 5 raised to the log base 5 of 4 is equivalent to 4. So don't overthink it on these problems. You can imagine that the base cancels out with the base and you just get the argument left over. In example 9, let's rewrite this as a single logarithm. I will start by looking at the first two terms. This is a negative, so I can use the quotient rule. This is log base 2 of a divided by b plus log base 2 of c plus log base 2 of d. Now we have all additions, and that means we could use the product rule. This is equivalent to log base 2 of a over b times c times d, and that simplifies to log base 2 of ACD divided by b. We just multiply straight across when we're multiplying fractions. In example B, we could use the same process, but you have to be careful. There's some negative exponents that appears in the problem, so you might have to factor out a negative. I, on the other hand, prefer to bring it up into the exponent. I again prefer to bring that negative into the exponent, and it makes my life a lot easier. So I can pretend there's a negative 1 in front of that natural log. And using the power rule, this is equivalent to the natural log of x raised to the negative 1 plus the natural log of y raised to the negative 1 plus the natural log of z. When I use the power rule to bring that negative into the exponent, the numbers in the front are now positive. This is good because I don't like the negatives. I would have to use the quotient rule. But since all of these are positives, we could just use the product rule. And according to the product rule, it's the natural log of negative 1 times y to the negative 1 times z. But we can't have negative exponents. So recall x to the negative n is equal to 1 over x to the positive n. It means I can bring that exponent into the denominator and it becomes positive. And that gives us our solution as the natural log of z over x to the 1 or just x and y to the 1 or just y. And that is it. Our solution is the natural log of z over x times y. In example 10, I am going to use that same strategy. I like to use the power rule. I'll bring that 6 into the exponent, that 1/5 into the exponent, and I get to choose either a negative 9 or a positive 9. I will choose a negative 9 because that makes all of the numbers in front of our logs positive. I'm going to choose a negative 12 here into the exponent. I know the textbook uses a different technique, and if you want to, you can use their technique by bringing just the positive 9 and the positive 12, and then using the quotient rule. That would work out and give you the same solution. So use whatever strategy you want. I can simplify this as log of a to the 6th plus log of b to the 1/5 power plus log of c to the negative 9th. Again, I'm bringing that negative 9. That's why this is a positive in front of the log. And this is plus log of d raised to the negative 12. And since all of these are positives, we can now use the product rule. The product rule states this is log of a to the 6th, b to the 1/5, c to the negative 9th, and d to the negative 12. But we can bring that negative exponent into the denominator, and this gives us our final answer. Log of a to the 6th, b to the 1/5. On the bottom here we have c to the positive 9 and d to the positive 12. This is a good solution. We could also write b to the 1/5 as a radical. So we could write our solution as a to the 6th, the 5th root of b divided by c to the 9th, and d to the 12th. Both of these answers are good. One is in exponent form and the other one is in radical form. Either answer is acceptable. In part B, there is a typo. We have 8 log base 2 of A minus 5 log base 2 of B minus 6 log base 2 of C plus 15 log base 2 of D. The D part got cut off, so let's add that D so we don't get this confused. And then I'm going to use that same trick I did last time. I love to bring those negative exponents in the top here. It just makes it easier so I don't have to switch between quotient rule and product rule. This becomes log base 2 of a to the 8th plus log base 2 of b to the negative 5 plus log base 2 of c to the negative 6 plus log base 2 of d raised to the 15th power. Since they're all positive, and that's what we want, it makes our life easier when we do the product rule. This is log base 2 of a to the 8th, b to the negative 5, c to the negative 6, d to the positive 15. We can bring all of those negative exponents to the bottom, leaving the positive ones on top. A to the 8th, d to the 15th on top, b to the positive 5, and c to the positive 6 is now on the bottom. And we can't simplify it any further. We're done with this problem. In example A, I can do what we did earlier, and that is to work with negative exponents. I can rewrite this as log base 5 of z cubed x to the negative 9 and y to the negative 4. Then we could use the product rule and expand this out as log base 5 of z cubed plus log base 5 of x to the negative 9 plus log base 5 of y to the negative 4. Then I can bring down the exponents to the front, and so we're just working backwards. And this gives us 3 log base 5 of z minus 9 log base 5 of x minus 4 log base 5 of y. This is using negative exponents. But we could use the textbook strategy, which is to use the quotient rule first. So I could say this is log of a to the 6th, b to the 7th, minus log of c to the 8th. This is using the quotient rule first, and then we could use the product rule next. This is log of a to the 6th plus log of b to the 7th minus log of c to the 8th. We don't really need the parentheses, but I like to use them so the reader knows that the argument includes the exponent. Bring these exponents now to the front using the power rule. This is 6 log of a plus 7 log of b minus 8 log of c. We are done with part B, but we didn't use negative exponents. We used the quotient rule first, then the power rule, and it gets us the same answer. So you can use whatever technique you want. I like the negative exponents because it avoids the need for multiple rules, but you can use whatever technique you want. The base change formula. For any positive real numbers, a, b, and x, a, b not equal to 1, the log base b of x is equal to log base a of x divided by log base a of b. How is this formula useful? Well, on our calculators, you'll see there's a natural log of x and there's a log of x option available. So I could easily find anything with a base of e for natural log or a base of 10 if I wanted to with a calculator. But if you're presented with something that is a base of 3, you can't do it on your calculator unless you use the base change formula. Let's look at part A. We have log base 3 of 125. Most calculators don't have a base of 3 on their calculators. So what we need to do is we need to rewrite this as log of 125 divided by log of 3. This is base 10 and my calculator has base 10 on it. So I could write on my calculator log of 125 divided by, and when you divide you want to be careful, you want to make sure that the entire numerator is dividing the entire denominator. So I like to use parentheses here, and so the calculator does the whole numerator divided by the whole denominator. So log base 10, or just log of 125 divided by log 3 gives us 4.395. So this gives us approximately 4.395. That's because my calculator has base 10 in it. But you can easily use natural log. This is equivalent to the natural log of 125 divided by the natural log of 3. Try it out with your calculator and you should get 4.395. Let's try it again. The natural log of 125 divided by the natural log of 3. It gives us the same answer, 4.395. So it's up to you. Which one do you want to use? Do you want to use log on your calculator, or do you want to use natural log? It will give you the same answer with the base change formula. I'm going to stick with natural log. I just find it a little bit easier to use, but it's really a matter of preference. In part B, to find log base 7 of 400, I'll take the natural log of 400 divided by the natural log of 7 on my calculator. We'll take the natural log of 400 divided by the natural log of 7, and it gives us 3.079. This is 3.079. And that is how we use the base change formula. And if you want to check your work, you can. You can use your calculator. This is the exponent that we got. So what we're saying is 7 raised to 3.079 should be close to 400. The reason it should be close to 400 is we rounded to 3 decimal places. So let's check it out and make sure we got it right. 7 raised to the 3.079 should be close to 400, and it is very, very close. It's not exact because we rounded. We can check our work for these problems if we choose to.